Bummer, I left my small font size chalk upstairs. Actually, can somebody do me the favor and get it from upstairs?
Yeah.
It's in my office.
Okay.
And the first, yeah. Yeah, just, the thin ones. Okay. Welcome, everybody. So what we're going to do for the next week, for the next 2 weeks, are basically random projection methods. And so I'll start with doing something fairly simple, namely just I'll briefly rederive some version of a Chernoff bound for binary random variables. And so it's going to be a multiplicative bound, so I'll show you that in a moment. And after that, and the main reason for doing this is because I want to give you a refresher on the exponential method for computing tails. And once we've done this, we'll go and look at random subspace projection methods. So there's a very nice paper by Dasgupta and Gupta from essentially 2002, which says something like an elementary proof of the Johnson-Lillenstrauss theorem, and then a more effective technique by Achlioptas, which doesn't exactly require orthogonalization anymore. And this is essentially going to lead us into this entire area of, well, working with random matrices, projecting onto them, and essentially keeping most of the interesting structure of the space that we work with intact. So the lead up is going to be binary random variables, going then to subspaces, then going to projections onto matrices, then going to entire subspace approximations of matrices. So this is the Halko, Martis, and Trop finding structures through randomness papers. Then moving over to more general concentration of major inequalities on matrices directly. So this is going to be something that's a fair part of Lester Mackey's PhD thesis. So the method of exchangeable Stein pairs is going to come in there. We'll look at concentration of measure using the Laplace transform, Alswede and Winter style for matrices. So this is roughly what I have planned out for this and next week. Let's see how far we get through that. Obviously, if you have any special preferences for some of this subject matter, yeah, don't hesitate. Let me start off by a couple of references. So one would be, oh, thanks.
White in color.
Oh, great. Awesome. Thanks a lot for that. Did you get it from my office?
No, I got it from 6th floor.
Oh, cool. Nice.
You got something in your office?
Yeah, so that's why. Okay, so then these will be yours now for TAing. Thanks. Awesome. Okay, so one of the references will be a paper by Trop. And this is called something like user-friendly concentration of measure for matrices. This would be 2012. Then there is a paper by Achlioptas. And this is database friendly projections. And this would be from around 2002. Papers are a little bit longer, but basically search for database friendly in Achlioptas and you'll find it. Then there's one by Gupta and Dasgupta. And this is basically on elementary proof that would be around also 2002. Then there's a paper by Lester Mackey et al. And this to some extent improves on the paper by Trop. And yeah, Trop is also co-author in it. It's about exchangeable Stein pairs. And basically, what this method of Stein pairs does is it's a much more refined and elegant way of dealing with what otherwise you would call a ghost sample. So usually when you derive a uniform convergence bound, you basically say, well, here's my sample, and then you make a copy of it, which is drawn from the same distribution. And then you start asking questions like, you know, how much does the sample and my ghost sample deviate from each other? This is usually how you deal with deviations from expectations. The notion of Stein pairs is such that you basically can make small random changes to random variables. So you don't have to necessarily change everything, and you can deal with most interesting types of dependencies between random variables this way. So that's why this is actually kind of a very nice technique. The original idea of these Stein pairs probably goes back to Saurav Chatterjee. At least he used it extensively in his PhD thesis. And I'm probably going to butcher his name here. So it's, yeah, a impressive and hard to read PhD thesis. It's very good. And then there's the paper by Halko. Martinson and Trop. And I don't know whether it's appeared already, but it's up on Archive. It's finding structures through randomness. Via randomness. And the title goes on for about 3 lines. But it's basically about random matrix and linear algebra tools. Also, Michael Mahoney has a bunch of tutorials up there. Then, yeah, Emmanuel Candace would be also one of the authors where you might look for results. And then there's also a guy called Piotr Indyk. And that covers some of the pointers that you might want to look up for essentially, you know, research related to what I'll be covering this week and next week. And more likely than not, all I'll be able to do is give you some ideas and you know, whet your appetite for what else can be done. And this is actually a fairly exciting area of the intersection between machine learning and statistics here. So the other thing that I completely left out are basically all the compressed sensing types of results. And so to relate a little bit how they go, so these types of results, these two, essentially state, well, you can take data, project it down to a low-dimensional space, and you're not going to lose much. The compressed sensing results go like, well, after I've projected things down, if the original data was sparse or had some very nice structure of some form, I can essentially recover that structure by solving an optimization problem. So it's basically, can we undo this projection and get back to the original data? So that's basically, the forward direction is is here. The backwards direction is compressed sensing. The direction of, well, can we apply this to matrices and more structured objects is essentially in here. Now the obvious question is, well, how much of this could you actually do if you had additional interesting structure in matrices? There are some results along those lines. For instance, Animan and Kumar has a result for reconstructing sparse matrices. There's also a lot of work that comes out of the UT Austin crowd. So basically they call it dirty models for whatever reason, because I guess they thought it was funny. So Pradeep Ravi Kumar would be probably one of the key people there. And then there's also Martin Wainwright. Okay, so these would be some of the people whose work you might want to look at if you're interested in this context. I mean, there's a lot more. This would be easily a class to teach just on these methods. Okay, so with that out of the way, let's start with a very, very simple warm-up. And my guess is some of you might have already seen this, but I just want to show you the basic idea in the simplest example possible, and then we'll just work our way towards more and more complicated examples. So this is going to be fairly math heavy for this week and next week. Last thing before I forget it, regarding the min hash that we went through in class, there was a very nice paper at dub this year. This is probably something you might want to read at some point. And this was a paper by Pham, den Mitzenmacher, and gosh, who's the third author? Pach. And they used a different sketch than the SimHash for comparing similarity. So basically what they did is they used a Bloom filter where rather than an OR, they use an XOR for inserting things into the Bloom filter, which sounds totally insane. But basically here's what happens. If you have an XOR, so if you have an OR and you insert a lot into your Bloom filter, the Bloom filter fills up very quickly at some point. It just saturates and all the bits are set to 1. So at this point, it's very hard for you anymore to find out what's going on. If you use an XOR, then basically the only bits that are set are those where you have an odd number of counts. So this is why they also call it the odd sketch. They were a runner-up for the best paper. I'm not sure they got it, because I skipped the closing ceremony, because they're usually very boring events. Yeah, went to a coffee shop and worked. Yeah, but basically, this was a runner-up for best paper, and quite justifiably so. So to be honest, I thought this was actually the nicest paper of all the candidates. And they do very nice analysis for how this sketch then saturates. So this helps a lot. For instance, if you have two sets which are very similar, then by inserting one and then inserting the other, you're zeroing out all the common terms. And so your sketch only contains the ones that are really different. So it's tricks like that that give you very high precision and recall rates for elements that are very similar, which otherwise for many sketches are actually really hard to deal with. So I thought this was a very, very nice and new idea, because it's basically a very different primitive from what people usually have done. So it's a paper worth reading. Okay.
So the retrieval is again, that's an OR.
Yes. So the regular Bloom filter is an OR, right? So once I've set the bit, it stays set. If I
meant
sorry.
Even in odd sketch to retrieve to see if an element was inserted.
No. So queries don't write. But
No, they don't write. But how do you check? Do you, I mean, for all the hashes?
you could do that, for instance. It varies. So they were mostly interested in actually looking at the number of bits that are set, as opposed to using it for the plain purpose of what a Bloom filter would have been good for. And then, so basically, just like how you can use a Bloom filter to actually find out how many unique elements you have. So their interest was more to do retrieval in the context where you have a lot of possibly very similar elements. So therefore, they don't use it as a Bloom filter, obviously, but they use it for similarity hashes. Okay, so basically look at that paper. In case you can't find it online, contact me and I have it on memory stick. Okay, so with that, a little bit as a background in terms of references, what to go through. And if you look at those papers, quite often there are slide decks that go with it. Let's now get to the math. So we'll start with something super simple. Let's say I have some random variables xi. This is just a simple warm-up. And that warm-up goes as follows. Sorry? Yeah, okay. So I have random variables xi, and they are drawn IID from from a binomial with some mean mu. So in other words, the probability that xi is 1 is mu, and it's 1 minus mu for it, if xi being 0. Okay, right? Very easy. And so now what I'm interested in is the comparison that, what's the probability that the empirical average will deviate from its expectation by more than some epsilon? So we did some of those things already earlier in class, but here now I'm actually going to go through a proof for this, because we'll need the elements of the proof over and over for the next few times. And it's quite instructive to see it in detail. Okay, so what I'm interested in is the probability that the sum of I going from 1 to n over xi is greater than, let's say, 1 plus epsilon times n times mu. Okay. So there's, simple thing that you might want to check. And, well, so now here comes the nifty trick. Of course, I could say that this is minus this. Okay, let's say greater or equal than 0. Let's just do that. Okay. So that's the same thing as the probability that e to the t times this entire expression here, sum over I going from 1 to n xi minus n mu 1 plus epsilon. Okay. Is greater or equal than 1. Right? So nothing has changed here, and this holds for all t greater than 0. Okay? So basically all I've done is I've just said, well, if this is greater or equal than 0, then the exponentiation has to be greater or equal than 1. And now comes the key trick. Let me use red crayon for that. Thanks for bringing all the colored crayons. That's awesome. The next lecturer will hate me because they won't be able to get rid of it. Basically, this, of course, is less equal than the expected value of this entire expression here. Right? Because whenever this holds, well, you know, taking the expected value, that's clearly an upper bound, right? Because whenever this holds, that argument here is greater or equal than 1 anyway. And the other thing that I'm also doing, and through that making my bound less accurate, is I'm also including all the cases where this is below, but then it'll have a value less than 1 anyway. So basically, by taking expectations, I'm strictly making this worse. The reason why I'm taking an expectation here is, so this basically deals with the worst case. But now, by looking at an expectation, I can basically look at the typical case for something that's a little bit more restrictive. Okay. So now I can just, this is of course a constant, so I can pull this out. And these random variables here are drawn independently. They're drawn IID. So I can write this as e to the minus n mu 1 plus epsilon. And then here I have times, now, actually I have a t here as well, e to the, of course I have e to the t xi, but I have this raised to the power n. I can do that because all those random variables are drawn from the same distribution, so therefore it's just that single expectation raised to the power n. Okay. Now, this is something we can compute very easily. Because, x takes on exactly 2 different values, 0 and 1. And we know that it takes on the value 0 with probability 1 minus mu. And so obviously 1 minus mu times 1, like e to the 0 is 1 minus mu. And then I have, in addition to that, e mu times e to the t. Okay. And that entire thing raised to the power n. Okay. Now I'm going to make my life a little even further easier. And this is also a trick that's very common. And the easiest way to memorize it is the following thing. Let me draw the exponential function. It goes like so. And here's the value 1. Here's 0. This is basically e to the x. And it's quite obvious that the function x plus 1 is an upper bound on is a lower bound on this. So 1 plus x. So what?
Yeah, would you mind rewriting the last step over there? Oh no, not the figure.
This one here?
Yeah.
Yeah. So we'll rewrite it in detail. So just if you bear with me for a moment, just look at this. So from that, so basically what we always have is e to the x is greater or equal than 1 plus x. This is such an amazingly useful result, and it's being used, and you just use it many, many times over to simplify your life. Okay, so let's use that to simplify our life here. So remember here we had one minus mu plus mu times e to the t. Okay. Raised to the power n, let's forget about that for the moment. So that's of course nothing else than 1, and then I have here plus mu times e to the t minus 1. Right? And this is, of course, less equal than e to the mu times e to the t minus 1. Okay, the reason why I'm doing this is because by essentially approximately taking the log of this, right, that's basically what I'm doing here. This is an upper bound for the log. I can now get this multiplicative factor in here again. And so what I therefore have is that the entire upper bound, that the probability of deviation is bounded by exp of, now here we have n times mu times e to the t minus 1 minus n times mu times 1 plus epsilon t. One plus epsilon t. Okay. Got that? Okay. Now, all we have to do in order to make this bound tighter is to minimize over t. So this is a standard technique, and we're going to see it afterwards for much more interesting distributions. But basically, the steps that we saw here, and we'll see afterwards again, is first of all, exponentiate things and take the expectation. Then simplify the moment bound such that you can actually efficiently optimize over it. Then optimize over this moment bound with regard to this free variational parameter that we have. That's what we're going to do now. So what we'll get, then plug that back in and solve for the rest. Okay. So now let's optimize over this variational parameter. So dt of, and so basically we need to make this as small as possible, e to the t minus 1 minus 1 plus epsilon t. Well, that's simply e to the t minus 1 plus epsilon. In other words, t is log of 1 plus epsilon. Okay. Now plugging this back in here, we have e to the t minus 1 minus 1 plus epsilon t equals, for this t star, well, we know what e to the t looks like. Actually, we know what e to the t minus 1 looks like. This is just epsilon minus 1 plus epsilon log 1 plus epsilon. And now we're going to compute the Taylor series expansion here. And you can do that in Mathematica or by hand. So doing it by hand. And the good thing is you'll see that you actually get an alternating series. Okay. To check that we do get an alternating series, let's just do it on the side here. Which we're going to expand around 0, right? So for epsilon equals 0, this is 0. So for 0, we get 0. For 1, well, we get d epsilon of this term. So we basically get log of 1 plus epsilon plus. So we're expanding this expression here. Actually, we could expand everything together. It wouldn't really matter. Plus 1, because we have 1 plus epsilon over 1 plus epsilon. So this at 1 is 0. At 2, we already can see what's happening, because here we just get 1 over 1 plus epsilon. So this is 1. And then actually, as you continue, I can tell you already now, it's going to be minus 1/2 plus 1/3, and so on. Because from here on, it's essentially the series expansion of the logarithm that kicks in. Right? So all we've done is we've just taken the Taylor series expansion of the and just shifted it by 1. You could have also seen it directly here by having the series expansion there and just shifting adjacent terms. Right. That would have been another way of doing this. Okay, now, what does that mean? It means that this is less equal than minus 1/2 epsilon squared. Because, well, this term will cancel. Okay, sorry, we have a 1 here. So that means these two terms cancel out. And this means that we have a factor of 1/2 because it's this Taylor expansion. Okay. And that's that. Okay. And then from there on, we have alternating signs, so we know that it's an upper bound within the radius of convergence. Okay, good. So what did this give us? Well, we now have an upper bound to plug in here. And we get that the probability of deviation, so this is a relative bound, I equals 1 to n xi minus 1 plus epsilon n times mu is less equal than e to the minus 1/2 n mu epsilon squared. Yes, that may not be the optimal factor, but you've seen now how you can get a very basic tail bound. So there's absolutely nothing magic in those Chernoff bounds. So just to recap the steps, step 1 was this here. Step 2, the expectation, which you can now make component-wise. Step 3 was this upper bounding. And that's kind of optional, but it simplifies your life a lot. And step 4 was this here. So we'll see exactly that same procedure repeated over and over again. So the reason why I'm showing it to you is because you might have a problem where standard bounds don't fit, and you can maybe derive a new bound of your own through that. Any questions so far? there are more elegant ways of getting one of those bounds. So basically, one of the tighter versions is by going through the entropy. And this, for instance, will give you packed Bayesian bounds and other things. But this is also a very convenient technique. Yeah?
If you use a high-order expression, I don't think you'll get anything better in terms of the rate, right?
You can get slightly better. Well, you're not going to get a better rate, because that's really what dominates your rate. So in other words, what you'll get is that epsilon is order 1 over square root n. However, you actually get some correction factors of third or fourth order, and that will give you something slightly tighter. I mean, we also left some things on the table here, right? We made this approximation. It's not going to change the rate, but what it basically means is that and this is also relative Chernoff bound, so for absolute terms you might get something else as well, and so on. So there is an entire Wikipedia page on Chernoff bounds, and there are probably about 10 on that page, and they're all of very, very similar flavor. So probably before you derive your own, just make sure that the one you need isn't already there. There are probably another 5 or so in the probabilistic method book by Noga Alon and Erdős, Alon, and I forgot who the third author is. Sorry, probabilistic method or probabilistic lens. This is. I have a copy in my office. So this is very much not a computational book, but a statistical book. This has another half a dozen such bounds in there. Basically, use those first. So I didn't go through this just for that Chernoff bound. I mean, there would be probably something more like 10702 to teach it in there, or 10705. But it's for what comes now. Yep.
I don't know if this is true or not, but then wouldn't you conjecture that if mu was really small,
yes,
then the variance is actually also really low, and so Bernstein should give you actually a better bound?
Yes. So Bernstein will give you better bounds? Yes.
When mu is small?
Yes. So I mean, this one at least will give you a multiplicative bound. So if you look at the standard Chernoff bound, which is additive, that one will be quite horrible for small probabilities. This at least is a multiplicative one. The reason why I did it this way is, first of all, it just looks, it's a bit different from what you've probably seen. Secondly, all the bounds that we're going to derive now are going to be of the multiplicative kind. The reason why we'll be deriving multiplicative bounds is because what we want to do is we want to get bounds for embeddings of data, right? And if I have data that I'm embedding into a high-dimensional space, I care about multiplicative accuracy, because I don't want to have to pre-specify how all the distances behave. Because I might have some very small distances, some very large ones, and I want to make sure that all those distances are well embedded. Okay, so that's basically why I derived it in a multiplicative flavor, and my guess is there are probably a dozen or so different, more or less elegant proofs on different types of those tail bounds. This is just the technique that we're going to use a few times over and over. And so it's a useful technique to know. Okay, good question though. Any other questions? Okay, so the first application is going to be with regard to low-dimensional embeddings of data. So here's the problem. Suppose I have some very high-dimensional data. So data lies in some space R to the D with a very big dimensionality. It could be infinite dimensional, albeit in this case, I don't really know of a very good statistical technique for getting my hands on this. This would be a really cool research problem if somebody managed to solve this. We touched upon this a little bit when we looked at random kitchen sinks and so on, but in general, the infinite dimensional problem is unsolved. I mean, you can get somewhere if you have pairwise distances or inner products, but basically, I have those points xi are in this, possibly very high dimensional space, and I want to find a projection P such that P xi minus P xj, the norm of this, is going to be within an epsilon factor and likewise that I have a lower bound of 1 minus epsilon xi minus xj. So in other words, this is an approximate isometry, and I want this to hold for all I and j pairs. So one thing that you can infer immediately from that is if I get this, I can also do a good job for inner products, right? Because there's a relative bound, and I just, adding a couple of those inequalities together. So you basically use the polarization inequality, and you're done. So actually, I'm going to use squares here to make my life a little bit easier. But to see why this immediately has to then hold for inner products, all I need to do is for two vectors, I just take, well, the vector x plus x prime, and I want to make sure that this one is well behaved. So I get this, and I get the bound for x minus x prime, and this is well behaved. So then the sum of those two is, well, actually the sum doesn't really help much. But I can get this for that one. Okay, let's see. Well, I get it for each individual one. And, sorry, no, that doesn't go through. The problem is if you take differences, I mean, you can prove it directly for inner products. That definitely works.
So, if you expand the difference, you get like norms and dot products, and the norms are like special kind of distance.
Well, the problem is that basically, well, yes, you could do it. You could do that as well. That you basically derive the distance matrix from that. But the issue is, if I have two of those inequalities and I subtract them from each other, then I have one plus epsilon and one minus epsilon, and things might cancel each other out, which isn't so good. Right? So that's the issue. Yeah. So unfortunately, that doesn't work. So, sorry. Actually, it should work. Yes. Yes. No, it actually doesn't. Yeah. Anyway. The point is, I'm interested in preserving those pairwise distances. So what? Yeah. So now there's a couple of things that I could try to preserve that, right? So one thing that I could, for instance, do is I could run PCA. Right? And, well, right, then, look at the covariance matrix, look at the largest directions of variation, and that wouldn't necessarily help me very much because well, I need to actually approximate all pairwise distance as well. If you were to run PCA, you would know that if I keep k terms, then for the k plus first up to the last term, the residuals cannot be too big. But that's about the only thing that PCA would really give me. So what I'm going to show you is now a couple of randomized techniques that will work actually in a way better than PCA. Okay. So the first strategy is we project onto a subspace. Because if you think about it, that's still better than just projecting onto a couple of random directions. And the key insight in how to prove these types of bounds is to actually first prove that for a random vector, the length is approximately preserved. Because if you think about it, this guarantee here just means that for some random vector xi minus xj, the length is approximately preserved. Now, how many such pairs do I have? Well, I have, if I look at all xi minus xj's, I have n times n minus 1 over 2 pairs. Right? So therefore, if I can show that such a guarantee holds with some probability delta, then I can make it obviously hold, sorry, 1 minus delta, I can make it hold with 1 minus n times n minus 1 over 2 times delta. Right? So I can then just apply the union bound because it has to hold for each of those pairs. And then in summary, if it holds for all of those and still with a small enough probability, then I'm fine. So therefore, we can reduce this to 1 minus epsilon norm of x squared less equal than px squared less equal than 1 plus epsilon norm of x squared. Right. And then just apply it n times n minus 1 over 2 times. Make sense? Good. So now the next step is going to be that we actually can restrict ourselves to unit vectors or vectors that are reasonably well behaved according to some distribution. And so the first time, so this is in the paper by Gupta and Dasgupta, we are going to restrict ourselves to vectors that are Gaussians, and where we go and pick, let's say, the first n out of k dimensions. And then we're going to check whether this projection will be in good shape. Okay, that's essentially the idea. So if you think about it, we have this vector x. Whether I have a radial component to it or not doesn't really matter for that relative bound, because it's a bound that will hold. Basically, if my projection holds for any vector, then it will hold for a multiple of that vector too. Okay. Now, since we have isotropy, I might as well prove that this holds for Gaussians. So that's the idea from the Gupta and Dasgupta. Later on, in the paper by Achlioptas, we'll show that a similar technique holds not just by projecting onto a subspace. So let's say this is here the subspace. And this, with suitable rescaling, should be related to that. So in the paper later by Achlioptas, we basically show that we only need a couple of estimators of the length of x, and we just average over that. And that will also be well behaved. So this is then going to be closer to the Halka-Martins and Tropin subspace algorithms that we use for matrices. Okay. So is that idea sort of kind of clear? Good. Well, let's get to it. Because once the concept is clear, the rest is actually fairly easy. Okay. By the way, does everybody know how to actually get a random subspace and project onto it? Let's say if I told you, find me a random k-dimensional subspace to project onto it. Does everybody know how to compute something like that? You could pick k-Gaussian vectors. That's very good. And then you'd have to pray that they are not linearly dependent, which they won't be, because usually k is going to be much less than n. And there are good theorems that tell you that this is actually going to be good. So we'll actually encounter such a theorem later. Or at least there will be theorems also of the form, well, it's good if you ignore the smallest ones, or at least most of them are going to be well behaved. So there are various theorems of that form. So the Wigner semicircle law is an example of that from, yeah, probably about 60 years ago. But basically, just pick k random vectors and also normalize them, and you're done. So in practice, this means if I have some z with zi drawn from a normal distribution with zero mean and unit variance, then, of course, and assuming that this z is in R k by d, then it follows that something like p being square root n over k, that's just for length rescaling such that things are okay, times, because we basically only pick k of those n dimensions, so we need to make good on that, and so you can immediately see that where this comes in. Then times z transposed to the -1/2 times z, that this will be a good projection. Okay. So that upfront factor we'll deal with in a moment, but this basically projects onto the subspace. And this matrix will clearly will have orthogonal rows, but it does obviously not have full rank. Right? Okay, so this is clearly a k-dimensional object. Computing it is very cheap because you just form the inner product, and then, for instance, you use a Cholesky factor. Yep.
What's the difference between, say, computing like k by d Gaussian matrix and obtaining normalizing them so that they are orthogonal versus, say, doing something like the QR on the Gaussian in order to get another orthogonal projection, and how would those behaviors?
So any rotation on this would do. So you could also, also normalize z directly. You could do that too. So either way is fine. Basically there are, you can immediately see any rotation that I apply here is going to leave the system unchanged. And so those various factorizations that I referred to, and also the one that you mentioned, would be just yet another rotation, and it's very much a function of whichever you can actually implement the fastest and whichever is numerically stable. So there's not that much of a difference. Basically, use whichever you have in a fast library. Okay. So now the first thing to notice if we think about Gaussians, right, is, well, if you were to take a random Gaussian and project onto a lower dimensional space, that's just like, since Gaussians are spherically uniform, you could just say, well, what's the length of the first k Gaussians relative to all the other ones? Right? That's equivalent to that. Because Gaussians are spherically uniform, if I draw from one, I can either rotate, the projection, or I can rotate the data. So those two are completely equivalent to each other. And that holds quite nicely in that case. And so what I'm basically asking is, therefore, what's the probability? So this is the key trick that I need to prove, that k times sum over I going from 1. Okay, actually, let's just write it like so. 1 over k, I going from 1 to k chi I squared is less equal, let's say without loss of generality, 1 over d sum over I going from 1 to d chi I squared, and then we also pick some coefficient, and here I'm just going to have that coefficient as beta, and so beta is greater or equal than 0, right? Okay. That's one of those results for basically beta is 1 plus epsilon. This is just to make my life easier, not to write 1 plus epsilon all the way through. And also to stay consistent with the notation in the paper by Dasgupta and Gupta. So in case you want to read up the proof in detail, that's where you can find it. Okay, good. So now we apply exactly the same technique as what we did before. And, well, just to make my life a little bit easier, I'm going to multiply things over, right? So I basically can multiply by d and by k here. That's still equivalent. And furthermore, of course, those chi i's are drawn from a normal distribution with 0 mean and unit variance. Okay. And now we're going to use exactly the same trick again as before. So this, of course, is equal to the probability, and now we need to exponentiate things, of t times k beta sum over I going from 1 to d chi I squared minus, and here we have d times sum over I going from 1 to k chi I squared. And we need that this quantity here is greater or equal than 1. Okay. This was step 1 in our previous derivation, right? There's this one up there. Step 2, which is the key step, is taking the expectation. So just to make my life easier, I'm just going to write it out. less equal than the expectation of this quantity here. Okay, so what's different from before is before we actually had a constant in here. Here we have just random variables. But the good thing is I can actually partition this up, right? So this equals, and so of course d is greater than k, because if it wasn't, I mean, it would be kind of boring, right? So we'll have expected value of e to the, well, t times beta times now k minus d and we have that raised to the power of d minus k, because these are all the times x, of course, and that goes inside here, and so x squared, and then we have, in addition to that, times the expectation over x of e to the minus t d x squared raised to the power k. Right? So that's really just, looking at individual coefficients. The reason why I can apply to each of those random variables separately is because they're all independently drawn from the same distribution. And so, again, we can compute those expectations exactly. So now the expectation is a little bit harder to compute, but actually not that hard, because we all know how it works, right? We all know what the integral of e to the tx squared times e to the minus 1 over 2 x squared dx, which is for a normal distribution, 1 over 2 pi. We know how that works, right? So that's basically just minus 1/2. Right? I can just combine those things here, and I just have minus 1/2, 1 minus 2t, right? And so I get that this is basically nothing else than 1 over square root 1 minus 2t. And this integral only exists for t being less than 1/2. Because otherwise that immediately diverges. Okay. So now the next thing is just to plug this in here. So this is one minus, and then here we have 2t beta, well actually we have d minus k, and then we get the minus here. See, did we forget something here? No, we didn't really. But then we got the minus wrong. No, this is, yeah. Guys, I made a mistake and nobody caught it, right? You need to be a bit more attentive. Okay, so first of all, we had just beta k, d minus k, because for those random variables, nothing happened. And then for those here, we did have a d minus k and a minus here, right? And now it all works out. It's basically for all the random variables xi for which nothing occurred here, this was the only thing that we had. So we had 1 minus t k beta, right, to the minus d minus k over 2. That was the square root here, right? Let's go here. And then we have 1 plus t d minus k to the minus k over 2. Okay, good. And there's a 2. And we also have a k beta. Right. Okay, good. So now the next thing again that we do is we use this exponential trick from before. So this one up there. So it's exactly standard. So we get bounded by okay, so actually I can just skip all of this. Let's just make our life easier. So we have, well, you basically optimize over t, you get something very unuseful. But basically overall you have, because I want to get through the content a bit, k over 2, 1 minus beta plus log beta. Okay. So this is what you get for the upper bound. You get a similar quantity for the lower bound, which basically ends up looking more or less the same thing as this, which you can then expand a little bit further into this equal then, if we expand beta is 1 plus epsilon, we get basically a e to the minus k over 2 epsilon squared over 2 minus epsilon to the 3 for 3. This is what survives from the Taylor expansion. Okay. So, and for the corresponding lower bound, so for the probability that, you know, this term is less equal than k 1 minus epsilon times all this holds, right? We get something that looks very similar, and basically it's going to be e to the minus k over 2 epsilon squared over 2. And we don't need that last term here. We just pay that for the upper bound. Okay. So there's a fair amount of detail in the Achlioptesin, sorry, in the Gupta and Das-Gupta paper, but I figured this should probably do. Does anybody want me to go through the step going from here to there? Because basically all you do is you upper bound this by e to the minus 2t beta. Likewise here, e to the 2t d minus k beta. You then optimize over t. You get the optimal value for that. You plug it back in, and you get that. So that's why I went through it for the simple binary random variables part, because it's not particularly instructive to, other than just the fact that it's the same technique. Okay, good. So now that we have this, all that remains is just to make sure that we pick an epsilon that's large enough that if we multiply this quantity here by 2 times that combinatorial quantity here, n times n minus 1 over 2, that this is less than 1. Okay. If I do this, then I'm home. The reason for that is as follows. Because I mean, effectively, what they specify is not a one-shot algorithm, but a randomized algorithm which, after invoking it often enough, will give you a good projection. So this is also different between this and the Achleoptis paper later on. Okay, and with that you get slightly tighter bounds. So what we want is that n times n minus 1 over 2 times 2, because we need an upper and a lower bound since we need to have good relative bounds, times exp of minus k over 2 epsilon squared over 2 minus epsilon cubed over 3, that this here is less than 1. So an easy way of doing this is by just replacing this by n squared and setting this equal to 1. Because in that case, I have basically 1 over n probability left. Right? So basically, there's a non-zero probability that this approach succeeds. And, sorry, n squared. And so, working this out, I'll get that k is greater or equal than 4 log n over epsilon squared over 2 minus epsilon cubed over 3. That's all I really need. So you can see this by, if you take the log, right? So if you take the log, then we basically have 2 log n minus k over 2 epsilon squared over 2 minus epsilon cubed over 3 equals 0. So we move this over here to the right-hand side, divide by that, multiply by 2, and we're done. Okay. So what I now have is an algorithm that, with probability of at least 1 over n, will give me an embedding that has small distortion. That doesn't sound too great. One way of getting a slightly better bound, for instance, something that succeeds with probability 1/2, is just making this thing here 1/2. So basically, or in general, you know, some delta. And then all you'd get is just you'd get this basically minus 2 log delta. And then you have it succeeding with a higher probability. So basically you have a small additive constant to that. Okay, so once you do that, you have a good projection, but it's actually a very expensive algorithm, because it means that you, in order to design this algorithm, you first have to actually generate your subspace, you then try it out on all of the data, and only in the end you'll find out whether you got lucky. And on top of that, you need to generate all those things, you need to perform a Cholesky factorization and all of this. So it's a very, very costly, very much classical conservative style algorithm. What we'll see on Wednesday, and this is just going to be the warm-up, is that by picking a random matrix of Gaussian entries, or actually of entries that are quite bizarre, namely one matrix might have entries of just plus minus 1 chosen at random. Another one might have entries of either square root 3, plus minus square root 3 or 0. And so those would be chosen with probability 1 over 6 each, and those with 2/3 respectively. Or I have x drawn from a normal distribution, that in any of those three cases, I will get an algorithm that basically is as good as this. And that doesn't require, pre-normalizing things. The reason for this happening is that in high dimensions, random vectors are more or less orthogonal to each other anyway. So you don't really have to do much work. The other reason is that random vectors, when suitably engineered, will give me good estimators for the length of a test vector. Okay. So with that, I think I need to conclude now, because otherwise somebody else will already come in. Any questions?